Hi, in this video, we're finally going to take our first step into exciting quantum computing world. Our topic is, what is quantum computing? So yeah, quantum computing has many fundamental laws, experiments, all the technological stuff, coding part. These are all the steps that we're going to take further in this course. But first, let's think about what is quantum computing and why are we learning about quantum computing rather than just learning about classical programming? So quantum computing is basically a computing technology that's been able to solve certain problems that classical computers cannot, or even if they can, it will take thousands of years for them to solve. But instead, quantum computers can actually solve them just in seconds or minutes. How insane is this? So in this case, we may think of quantum computers and quantum computing as the technology of the future. Quantum computing will be able to change the world, all the technology that we know it. So in this picture, you can see the quantum computer that puts all the potential in it. So in this case, I think it'll be better for us to look about all the sneak peeks about quantum computing. There are three quite important laws about quantum computing. The first one is superposition, there is quantum entanglement, and there is quantum interface. So let's start from the beginning. What's superposition telling us that? As we saw on the previous video, bits, the classical computer's smallest unit of information can only store two values, either 0 or 1. So it's like a switch. It could be off or on, 0 or 1. But there's the hook. In quantum computing, we have bits called as quantum bits, also referred as qubits. So the thing about qubits is that they can store the value of 0 and 1 at the same time inside. So this enables us to use the exciting opportunity and the power that's coming from all the quantum physics into quantum computing and the code that we're going to write onto quantum computers. So there's a famous experiment about the superposition law that is also called as Schrödinger's cat. So we're going to see this in the upcoming videos about the course, but here's a sneak peek. There is a 50% chance of cat being dead and 50% chance of cat being alive. We're good. But what if I tell you that it's happening at the same time? It's interesting, right? So we're going to see this in the upcoming videos on this course. The second law we have is quantum entanglement. So quantum entanglement is telling us that quantum states can interact with each other no matter how far they are. Even if one qubit is, let's say, in the A spot of galaxy and the other qubit is in the B spot of the galaxy, they can communicate, they can interact with each other no matter how far they are, no matter distance. We also have a quite fun and engaging experiment about this that we're just about to see in the upcoming videos. The third law we have is quantum interference. Quantum interference tells us that quantum particles, qubits or quantum gates, could also act and interact with each other just like waves. So this is kind of physics related, but please don't worry. We're going to cover this with real life examples, and I'm going to try to make it as engaging as possible. I promise. Okay, so we saw about bits, and you recently heard about the concept called qubit, quantum bit. But let's dive deeper into that. What is quantum bit? It's the smallest information unit in quantum computing. So a qubit could store the value of 0 and 1 at the same time. So this is where quantum computing takes its power. It's the smallest information unit in quantum computing, and we can store much bigger and much more complex information, data, with qubits. So that's why we're learning quantum computing, and that's why we think that quantum computing will be the technology of the future. So in the kind of complex equation above, we see a value of psi, which is calculated as square root of alpha times 0 plus square root of beta times 1. This may seem a little complex. Please don't worry. This is actually quite easy, and we'll get right into it. This is just a video that to understand how quantum computing works and why are we in this course in the first place. So everything that you're seeing here and you kind of feel it's complex will totally mean everything to you. And please don't worry, you'll understand it, I promise. And I'm going to try to make it as engaging, as fun as possible. A qubit meets superposition, entanglement, and interference love, the three important things that we see in the previous slides and that we're about to see more detailedly and with all the real-world examples and experiments about in the next videos. And in the image, you can see an infographic about the differences between bit and qubit. So as you can see, a bit could either store the value of 0 or 1, but a qubit could store the values of 0 and 1 within at the same time. So this is where quantum computing, the quantum coding, takes its power and why it has the potential to be the future technology. Hi, in this video, we're going to start our exciting experiment series. After talking about the important three fundamental laws of quantum computing, now we can actually start learning about the experiments that change the quantum world. We're going to start with the wave-particle duality. So before talking about the wave-particle duality, I think it will be better for us to understand who is de Broglie. You might wonder, why are we learning about this scientist? Because de Broglie has so many contributions to quantum world and wave-particle duality experiments, learning about Louis de Broglie will be much better for us to understand how we can approach the quantum physics and thus wave-particle duality. So Louis Victor Raymond de Broglie was a French aristocrat and physicist who made groundbreaking contributions to quantum theory. In 1924, his PhD thesis, he postulated the wave nature of electrons, and he suggested that all matter has wave properties. This concept is also known as Broglie hypothesis, an example of wave-particle duality, and forms a central part of the theory of quantum mechanics. De Broglie won the Nobel Prize for Physics in 1929, after the wave-like behavior of matter was first experimentally demonstrated in 1927 that we're just about to see in the next slide. So we can understand about de Broglie is that he won the Nobel Prize. He made groundbreaking contributions to quantum theory and quantum physics, and he worked in wave-particle duality. So he actually worked about this experiment to prove wave-particle duality. So as you can see from the meme, we can understand that electrons can act like both wave and particles. So this is actually one of the first milestones about quantum physics too. According to this experiment, we have an electron beam gun, which is producing super intense electrons in a super fast amount of time. And there's also a double slit on top of electrons. So once electrons pass this double slit, actually, we was expecting to get two lines of electrons in the screen because we know that electrons were particles. But after doing this experiment, we started to get some interference pattern, some wave pattern from electrons. So in this case, de Broglie asked, if electrons were particles, we were supposed to get two equal same lines, but we get a wave, we get an interference pattern. So in this case, he decided to write a thesis on wave-particle duality. After doing that, as you can see from the introduction part, he won the Nobel Physics Prize. And this is quite important for both quantum theory and quantum physics. And as you can see from here, after de Broglie proved that, and all the scientists made insane contributions to quantum physics, we were actually able to develop quantum computing, quantum coding, and maybe had the potential to develop the technology of the future.